Today we are going to talk about STEM, scaling transformers with embedding modules. The name itself is the main idea here, and the subtitle makes the punchline explicit. Stop paying for constant matrix multiplications and start loving the lookup table. The phrase, the STEM solution, is setting up STEM as a concrete replacement inside the transformer architecture, not a training time hack or a new optimizer trick. Conceptually, it is about swapping heavy matrix multiply work for a token-indexed embedding lookup. And this is what is shown in paper by authors like Sadukun, Cao, Dong, Zhao, and collaborators from Carnegie, Mellon University, and Meta AI. On the right, the 3 AM training loss panic graph is a common occurrence during mixture of expert, aka MOE training. The loss suddenly spikes even when nothing obvious changed. That instability often comes from uneven routing. Some experts get flooded, while others barely see data. So underutilized experts stay undertrained, and the optimization lurches. The routing diagram vibe hints at the system cost. Tokens are being shuffled to whichever expert lives on another device, and that all-to-all traffic eats bandwidth. Finally, the last bullet point is the trade-off. The finer you slice experts, the more knobs, load balancing, and operational tuning you inherit. Wait, isn't this just an address in the standard SWI GLU feed-forward network, aka FFN formulation? This epiphany comes from 3 claims. First, feed-forward networks act like key-value memories. You feed an X, and the network retrieves some stored information. Second, the up projection, WU, is basically manufacturing a key, an address vector, that helps locate what to pull out later. But then comes the uncomfortable part. If the token ID already tells us which entry we are dealing with, why spend a massive matrix multiply just to rediscover that address? That sets up the punchline. Token identity can directly select a stored vector, replacing that heavy up projection multiplication with a simple lookup. On the left, the dense feed-forward network, old Pensator-tooled path is the classic feed-forward block. You take the token representation and push it through big learned matrices, which means heavy matrix math every time a token passes through the layer. On the right, the STEM, new, column swaps out that expensive step. Instead of computing the up projection with a dense matrix multiply, STEM uses the token ID to index a static embedding table U. Basically, just grab the file for that token and use that vector directly. Notice what does not change. The gate matrix WG stays dense and learned, so the model can still modulate features based on the current hidden state. And the down projection WZ also remains a standard dense matrix to map back to the model dimension. Only the up projection is replaced by the lookup. To make this approach practical at scale, STEM incorporates several critical system-level optimizations like CPU offloading, async prefetch, token deduplication, LFU caching for communication reduction, and decoupled parallelism strategies. The overall idea is that the big embedding tables do not have to sit in GPU memory all the time. They live in CPU and RAM, and then the system prefetches only the rows it needs over to the GPU right before they are used, so GPU compute can keep moving while data is streamed in. Also, in a batch, the same token can appear many times, so we do not need to send it 500 times. We send it once, then reuse it for every occurrence. The efficiency line at the bottom quantifies the payoff. By offloading the replaced component, about 1/3 of the feed-forward network parameters are removed from active GPU memory. In this graph, we are plotting validation perplexity, lower is better, against training tokens. The joke line about a heart attack points to the hash-MOE curve. It does not just trend down, it lurches with sharp spikes that signal unstable training. The STEM curve is the opposite, smooth, steady, and predictable, which is why it is labeled Zen. Those shapes connect directly to the bullets points. STEM runs with 0 loss spikes, and it reaches lower perplexity using fewer flops, meaning less compute for the same or better quality. And this is not a toy result. It is demonstrated at both 350 and 1B model scales. Training return on investment, or training ROI, is defined here as a simple ratio: accuracy divided by flops. So every bar on this chart is answering one question: how much accuracy do we get for each unit of training compute? The comparison is between the dense baseline model and STEM full. The STEM full bar is higher, and the slide summarizes that as a 1.33x improvement in training ROI. In other words, for the same compute budget, STEM delivers more accuracy, or for the same accuracy target, it needs less compute. That efficiency comes from the architectural change called out at the bottom. Per token flops drop by about 33% because the up projection compute is removed. On the top, the dense feed-forward network picture is drawn as a crowded geometry. Points are packed together. So many pairs end up with high cosine similarity. When everything points in similar directions, concepts overlap, and it becomes hard to isolate the one you want, like trying to find your car in a packed parking. That crowding creates interference, because nearby representations can get confused. On the down, the STEM embeddings are spaced out with more personal space. The pairwise cosine similarity is lower, so concepts are more distinct and easier to separate. The takeaway is the same. Less interference leads to better knowledge storage capacity, more room for activities and distinct concepts. Interpretability and knowledge editing here comes from a simple idea. Embeddings are tied to token IDs. That means the model has a specific addressable slot, for example, the token Spain. We can point to where Spain token lives in the embedding table instead of guessing which weights encode the fact. The input prompt capital of Spain, tick-out, is tokenized. The Spain token triggers its corresponding embedding, and that embedding flows into the model's computation. Then it produces the output. If the model answers incorrectly, aka Berlin, instead of Madrid, the intervention point is clear. Adjust or swap the embedding row associated with the capital of Spain token with correct Madrid instead of Berlin, so the downstream output changes. That is what the quote means by surgical intervention without the mess. You edit the relevant representation directly without retraining broad weights or rewriting the prompt. Hacking the token length mismatch is about a simple but annoying constraint. Sometimes your source concept is one token, like France, but the target phrase you want is two tokens, like United States. The question is how to build a clean mapping when the lengths do not line up. The slide lists 3 practical fixes. Padding, called the filler strategy, adds an extra placeholder token so the one token source can be treated like a 2 token input. Copying, the clone strategy, duplicates the single token so both positions get something to map from. And averaging, labeled as the diplomatic solution, blends representations so the pair of target tokens share a consistent signal. The punchline at the bottom is the surprising part. All 3 work, and the model adapts almost immediately. For this graph, on the horizontal axis, context length, on the vertical axis, is the needle in a haystack retrieval score, measuring how well the model can find a specific piece of information as the prompt gets longer. The key idea written here is that longer context means more unique tokens will appear. On average, a plus 13% increase. With STEM, unique tokens matter because each distinct token activates its own embedding entry. So as you read more, and the prompt contains a wider variety of tokens, more STEM embeddings get pulled into the computation. That makes the model's effective capacity larger at test time, even though the trained backbone is unchanged. The takeaway matches the headline. More reading, make a model bigger. Okay, now welcome to the graveyard of failed approaches, the spot where researchers bury the tempting ideas that did not survive experiments and crown the winner. 2 headstones are called out. First, replacing the gate projection. That sounded symmetric, but it broke the point of gating. Second, additive embeddings. The slide even spells out the outcome. More flops and no gain. The text at the bottom explains why these approaches died. Think of the feed-forward network like mail delivery. The up projection creates the address. It decides where information should go. The gate reads the mail. It decides, based on the current context, what actually matters. Our winning choice is to make the address static using the token ID, but keep the reader dynamic, so context can still control what gets through. Here is the scoreboard, and the first line is the headline number on Knowledge-intensive tasks, performance rises by as much as 9 to 10%. That is not a tiny bump. It is a clear step up on benchmarks that depend on recalling facts and using stored information correctly. The next bullet point zooms in on reasoning, where the gains are especially strong. The slide calls out math specifically, and it also notes multitasking, meaning the model holds up better when it has to juggle multiple instructions or objectives at once. And the takeaway ties it together, simplifying or dumbing down. The architecture was, in this particular way, actually produced smarter behavior, not worse. Okay, time for final tally. Stability. STEM trains smoothly, without the sudden loss spikes that often appear when routing or load balancing gets messy. Efficiency. The model activates fewer feed-forward network parameters per token, and it can offload the large embedding tables to CPU memory, reducing pressure on GPU VRAM while keeping the backbone compute focused. Smarts means the model beats dense baselines on the hard tasks where extra capacity actually matters. Interpretability highlights a concrete win. Because the components are token indexed, you can trace behavior to something as specific as a Spain neuron, instead of guessing which expert fired. Long context line connects to the earlier retrieval plot. As context length grows at test time, you can scale effective capacity with it, rather than being capped by a fixed dense block. The bottom line is the claim behind STEM. It decouples capacity from compute, aiming to keep the benefits of a larger parameter budget without paying that cost on every token. For the full details, see the paper, STEM Scaling Transformers with Embedding Modules in 2026 by Sadukhan, Cao, Dong, Zhao et al.